Assalamu alaikum, guys. Today we're gonna talk about the last part of this course, which is columns, and this is going to be actually done in three parts. The first part, we're just going to talk about axially loaded columns and giving you some provisions as well. The second part will be talk about interaction diagrams, which is a result of the column being under both an axial force and a moment. And the last part, we will talk about what we call unsymmetrical reinforcement. From the title, we will only be discussing short columns. As you know, there's two types of columns. One is a short column and the other is what we call a slender column. Slender columns is usually the columns where buckling is involved, and if you remember during strength of material we taught you this ratio KL over R being the radius of gyration, K is a factor that depends on the support condition, L is being what we call the unsupported length. Usually if that is less than 22 for a braced frame where we have no, or for frames with side sway, then we have what we call a short column. Since we are only going to deal in short columns here, which means I don't have any dangers of buckling failure, you don't need to worry about this ratio because you will take that in RC2. Types of columns. Another types of columns we have what we call, well, when I said two types, short or long, that depends on the functionality of the column. Then we have types depending on the cross section and depending on how it is laterally reinforced. And the first type is what we call rectangular or square columns, and that's reinforced with what we call longitudinal bars and lateral ties. This is your longitudinal bar and these are your ties. Okay, if I look at the column from the top, this is my cross section, so these are again my transverse ties. The other type is what we call circular columns, and that's reinforced with longitudinal reinforcement and what we call a spiral reinforcement or lateral ties. So we could use both in there, but usually for circular columns the preferred reinforcement is the spiral, although you could use ties, but again the preferred one is the spiral because it's giving you more confinement, it's better to deal with. As I mentioned earlier, we call this the pitch, which is the distance between the spirals. Another type of column is what we call a composite column, and there we have what we call steel structural shapes. Like this is what we call an I-beam. So this is a main reinforcement also, and this is usually used for very high loadings. And we will not talk about that in this class. Our main part is going to be the first two type, not this one. But these are the column types that we have. So why do we have lateral reinforcement? Well, first of all, from a constructional point of view, it prevents the longitudinal bars from being displaced during construction. Usually, it is very hard to deal with longitudinal reinforcement, especially in columns, due to their length. So it's better if they are what I call caged together. So if I put a tie on, let's say 4 or 5, depending on my design, I usually call that a cage, and that's much easier to handle during in construction and much easier to put in place than if I would do it individually. The second advantage is it resists the tendency of longitudinal bar to buckle. Again, here, because they're very slender, so buckling might become an issue. So if I put lateral ties, I'm just decreasing the unsupported length by using these ties. So that's another use. The third use is again shear reinforcement, and you do need shear reinforcement in columns. so that's kind of a no-brainer. It increases the column strength by giving it more confinement to the column, and I will show that in the next slide, especially for spiral reinforcement. Why do I have, or what's the advantage of a spiral column, let's say, over a tight column? Again, with the spiral, again, because it surrounds the longitudinal bars much more effectively and efficiently than regular ties. So then it's better to handle. The second advantage, they confine the concrete inside the core better and greatly increase its resistance to axial compression. So let's think of it like that. So let's say if I have a cylinder, okay, and assume that I'm filling this with sand, right? So sand in itself, if I apply a load to it, it will collapse immediately. But if I put that in a cylindrical container, and let's say I'm applying a force P, obviously if it's loose sand, it will become dense up to a certain point where it would achieve maximum density, and then the sand has no, or the sand particles don't have any place to go. So what will happen then as I increase the load? Now that load will transfer to the cylinder walls. Okay, so as long as those cylinder walls hold, you will have no failure, right? And because it's a cylinder, we call these hoop stresses. And the spiral have the same, and this is analogous to the spiral column as well. As you start increasing the load, now the concrete inside that core, inside that spiral, now will refer all of its excess force, let's say, to that spiral. So that means this is an additional strength, by the way, which we don't account for. Okay, to us, once we reach that failure for concrete, that column is failed in our mind, but it really isn't. Okay, because some of that strength is now transferred to the spiral, which means what? Which means that they are more ductile. Okay, so if you, let's say, draw the force versus, let's say, longitudinal strain, then as you increase the load, it will go up like that. And here I'm talking about both spiral and tight column. It will go up to failure or ultimate load. Let's say this is my ultimate load. Now at this point, both the spiral, I'm going to say S, and the tight columns are the same. And then after I reach that ultimate load, you will notice that the spiral will kind of fail quickly, immediately. So you will have kind of a sudden failure in columns. For tight columns, okay, as the spiral now, that behavior depends on how heavily reinforced it is. So if I have a heavily reinforced spiral, it will probably go this way. If I have a light force spiral, it will go like that. So you can see there's this additional like that. So this is heavy, and by heavy I mean the reinforcement or spiral ratio. Okay, so this is heavy and this is light, still better than my tight column. Obviously the ACI code came with a spiral reinforcement ratio, which is kind of in the middle, and this is why I call the ACI reinforcement ratio, and I will talk about that today in the coming slide on how we are going to calculate that. So these are some of the advantages of the spiral columns. So now let's go into the nitty-gritty of how we do the column design, I guess. And what we have here is a column cross-section. So this is my column cross-section. The definitions: H is again the height, if you will. B is the width. Here D prime is still the definition of D prime is from the extreme compression fiber to the centroid of the compressive reinforcement, and D is still the definition of the distance from the extreme compressive fiber to the centroid of the tension reinforcement. Now again, here I'm just dealing with pure axial load, so you say, where's the tension coming from? Well, if there's a moment, then I'm going to have tension, but again, For now, there is no tension, so everything is still under pure compression, but the D still means what it means in flexure and the D prime as well. Okay, so I just want you to know that further down the road. But for this drawing that is in front of you, here I'm having a pure axial compressive force, which means if this is my centroid, then the load is applied right down in the middle at the centroid. Okay, now since I'm having pure compressive load, then the strain in concrete, as we learned before, will not exceed 0.003 per the code requirements, or 0.004, but we said we're going to use here 0.003. And we also said that for compressive, Whitney's block still applies, so I'm going to use the 0.85 F prime C. Okay, so this is now my stress. So if I wanted to know the forces, then for this steel right here, it's just going to be simply the area of steel, which I call A prime S, times the yield. For the bottom, well, it's not, well, let's call it for now bottom steel. It's going to be area of steel times Fy, and the concrete compressive force, which I'm going to call C sub C, is going to be 0.85 F prime C, the gross area, which is B times H, minus the total area of steel, which is simply the area of steel of this plus that. Okay, then my nominal axial force is going to be 0.85 F prime C, area gross, which is BH, minus the total area of steel, plus area of steel, and I usually sometimes call that C prime S, and I call that sometimes CS, okay, which is compression in steel, and this is compression in prime steel. So this is AS Fy. Then nominal force is going to be simply 0.85 F prime C times area gross minus area of steel plus the total area of steel times the yield strength. This is how I calculate the axial force in columns. Again, there's no moment here, there's no tension, pure axial force. Okay. Now, some of the provisions that we need to know about. Again, the same thing, your phi Pn must always be larger than the ultimate load, P ultimate. Now, P ultimate is the same, 1.2 dead Z, plus 1.6 live. Again, columns are going to be under axial forces, moment, it's going to be under shear, it's going to be, again, torsion might be an factor. So it holds all the, let's say, necessary forces on it. And phi is, as we taken it before, when I explained that to you during the flexure class, this is going to be, if it's a tight column, it's going to be 0.65. Phi for flexure, again, it's going to range between 0.65 to 0.9, again, from being tension controlled to compression controlled, which is from compression controlled being 0.65 and tension controlled being 0.9. Shear is just simply 0.75, and torsion is also simply 0.75. Whatever we took in the calculation about the moment, we are going to apply here as well. I mean, using the whole beta 1 or A equals C beta 1, the whole 9 yards, that I would say, that we took in flexure is also applied here. As far as shear calculation goes, whatever we took on the shear part also is applicable to the columns as well. And I'm going to do some small reviews to that in the coming slide as far as shear is concerned. Then there's another provision which is about the nominal axial compressive force. So here we're going to define what we call nominal axial force or maximum axial force. Okay, and this is, again, we have pre-stressed and non-pre-stressed. We are only going to deal with non-pre-stressed in this class here, and for that we have, again, tight column or a spiral reinforced column, right? So if we're only using ties and not spiral, then that Pn max is going to be 0.8 P0. Okay, if it's a spiral, it's going to be 0.85 P0. Now, P0 defined in the code is the same equation that we just developed before, which is the 0.85 F prime C, area gross minus the total area of steel, plus Fy, yield for steel, times the total area of steel, which is found in this code in the ACI right here. There is one caveat, though, that the value of Y shall not exceed 550 megapascal. So even if I have steel reinforcement that is more than 550, I cannot use more than 550. And for one main reason, concrete will not survive. It will fail long before we reach a yield stress of 550. Okay, so it will be crazy to use more than 550 anyways. So what you've noticed so far, so we said that my nominal force Bn is multiplied by phi, which again is, let's say for tight columns, is 0.65, right? And then this cannot be more than 0.8, so I'm multiplying 0.65 times 0.8 as well. So for a tight column, I'm limiting my maximum load to 80%, and of that 80%, I'm only taking 65%. Okay, so only in columns can we see that added level of safety factor. Why? Why do we do that? Well, first of all, and most importantly, obviously, is that the failure of a column is more severe and it's more detrimental to the structure. I can handle a beam failure. Okay, I can even handle a slab failure within limits, but I cannot handle a column failure. If a column goes, then the building is done. Okay, so that's the main reason. The other reason, obviously, it's more difficult to place the concrete and columns. If you go to any construction site and see how they pour concrete in the column forge, you can see how difficult that is and how narrow that is. It's not as easy as pouring concrete for slabs and beams. The third reason is also the failure in column, obviously, depends on the concrete ultimate strength, right? In beams, usually we wait for the yielding of steel to happen, correct? And that's how we do our design, and then failure will occur. In concrete, not so much. In concrete, in columns, excuse me, I'm relying heavily on the compressive strength of concrete. And that's the other part. Usually the compressive strength is not very well defined as it is for steel. So I'm adding that added layer of safety because of that. Okay. Now the other thing is columns subject to axial load only. Well, that's not completely true, although we are assuming that it is purely axially loaded, but we do know that loads shift, and as they shift, you cannot have a perfectly axially loaded column, so we must count for moment so slightly, okay, for it to be able to handle, right? The minute we see initially cracked or the other imperfection will also make it impossible for me to have a really concentric column, so I must count for some of the moment, which is in that added safety factor. Again, if I have one loading, forget it, you're gonna have a moment. If you column is part of a rigid frame, then you're also going to have a moment. So we always do, even if we there are some instances where the moment isn't that big or small, but we always count for about 10% of that for tension reinforcement, and I will get to that when we go to the interaction diagrams. Okay. Now let's talk about shear. So for non-pre-stressed columns, and for pre-stress, which we do not care about in this course, the longitudinal reinforcement should be at least 0.01 area gross and shall not exceed 0.08. So what he's telling me, I can have reinforcement ratios from 1% up to 8%. Although from a practical point of view, you usually should not exceed 4%. Because with 8%, steel becomes very congested and very hard to deal with, especially in these tight corners and joints where the slabs run into the column and the beams reinforcement run into the column as well. And with added 8%, that's too much to handle. So although the codes allow it, maybe you need it at some point, but again, usually 4% is more than enough. But the code allows it from 1% minimum. So even if you don't need any steel reinforcement, like we did in flexure, you still need a minimum reinforcement ratio, which is about 1% of the gross area. As far as shear reinforcement goes, we need to supply what we call AV minimum in the regions where my V ultimate is larger than half 5 VC. Okay, now 5 VC again is, you can take that either from equation A or equation B. Okay, whatever we took in shear regarding piers and beams is applicable to columns. All right, now what he's telling me here, if shear reinforcement is required, then AV minimum shall be the greater of A, and we use that, and B, and we use that in the design of shear for beams. Okay, my advice, always use shear reinforcement in columns, even if you don't need it. Even if your V ultimate is less than half 5 VC, just use AV minimum. You're not going to regret it. All right, moving on. As far as the ties, they shall consist of a closed loop of deformed bar with a spacing in accordance with A and B. So ties in columns must be closed loop. So I cannot have an open loop. I cannot have ties like that, like we have in beams. I cannot have it like this. Okay, it has to be a closed loop. Now the spacing between one tie and the other is A and B, clear spacing of at least 4/3 of the maximum diameter of the aggregate. The center to center spacing shall not exceed the least of 16 dB of longitudinal bar, 480 dB of tie bar, and the smallest dimension of the member. So let's say this is my column right here, and this is my B, and this is my H. Assuming that B is less than H, then the smallest dimension of the member is going to be B. If my tie is made out of phi 10, then I'm going to multiply 48 times phi 10. If my longitudinal bar, let's say, is 525, then that spacing is going to be 16 times 25. Okay, so it shall not exceed the least of. So I'm going to take the minimum out of these three and apply that as my spacing, and compare that with A, which is my 4/3 diameter of the aggregate, and then take the smallest of both of them. Another provision for my ties, it says that the diameter of the tie bar means I cannot use phi 8 in columns. I can only use phi 10, especially if they are enclosing phi 32 or smaller. If they are phi 36 and larger, I cannot use less than phi 13. We don't have phi 13 in Jordan, so obviously we must use phi 14 instead. Okay, so these are for the ties. Now, if I'm talking about the spirals, spirals, again, it's at least of 25 millimeters and 4/3 the maximum size of the aggregate, and it should not be greater than 75 millimeters. So the maximum spacing in spirals, or the pitch, should not be more than 75 millimeters. Okay, and it should not be less than 25. So the range for the pitch in the spiral is obviously between 25 millimeters and 75 millimeters. The only time for the 4/3 diameter of the aggregate plays a role if it's between 25 and 75. For cast in place construction, spiral bar or wire shall be at least 9.5 millimeters. Again, I cannot use less than phi 10 in shear reinforcement for columns, whether it's a tied column or a spiral column. Spirally reinforced. Okay. Now, there's another thing that we talked about when we had that drawing, if you remember. I told you, as we look at the failure, if I had a heavily reinforced spiral, it would go like this, and the light would go like this, and then set the ACI spiral. Well, that's the reinforcement ratio that I was talking about regarding the ACI. It's equal to 0.45 area gross, the gross area divided by the area of the core concrete, which is confined within the spiral, F prime C divided by Fyt. Again, Fyt shall not be greater than 700 megapascal. I will show you how to use this equation in example number 2. So just bear with me till we get to that. As far as detailing goes, for detailing, again, the concrete cover for reinforcement shall be in accordance with 20.51, which is the same table that I have provided to you during the lecture class. For columns, it's minimum 40 millimeters. Development length, whatever we took in development length calculation in which was the class before this, is applicable to the columns as well. Along development and lap splice length, and I said I'm going to defer to the lap splice length in column at the end of this class. Inshallah, if we have time, we will get through that at well. But for development length and lap splice, the longitudinal bars where I have Fy more than 550 megapascal, the transverse reinforcement, okay, shall be provided such that KTR, which is the value that we calculated before, same technique, shall not be smaller than 1/2 the diameter of the longitudinal reinforced bar. Okay, so that's if we have more than 550, I have to calculate KTR. Based on KTR, if that value is less than half dB, then I need to provide more lateral reinforcement. Minimum spacing shall be in accordance with 25.2, which is again like we took in the lecture, same rules apply. Minimum of 25 millimeters, or I believe it was 1/3 of the diameter of the aggregate, or the larger of more than 25 dB if it's more than 25. Now, another detailing issue is for non-pre-stressed columns and for pre-stress, which we don't care about here, the minimum number of longitudinal bars shall be A, B, or C. So that has nothing to do again with the 1% provision. So it's an added thing. So if I have triangular ties, I must use 3, which is at each corner. If I have rectangular ties, then I need to use 4, again at each corner. If I'm using spiral or the circular hoops, then I need to have at least 6 enclosed by spirals. Okay, and again I'm talking about the longitudinal. So if I'm having a rectangular tie, I need at least 4. Here's 1, 2, 4. Okay, if it's a circular tie or spiral, I need at least to have 6 longitudinal reinforcement. That's the minimum. And again, for triangle ties, it's going to be 1, 2, and excuse the drawing for my triangle. It's not triangle-y like, I guess. Ignore that. All right. Now, let's start off with examples. So, example C1, I want to design a square-tied column to support an axial dead load of 700 kilonewton, including own weight, and an axial live load of 900 kilonewton. Here I'm assuming 2% of longitudinal steel is desired. It's just an assumption. F prime C, I'm using 20 megapascals, and Fy is 280 megapascals. So like we used before, we calculate the ultimate load. The ultimate load is 1.2 dead load plus 1.6 live load, and it will give you 2,280 kilonewtons. Now we go to our Pn equation. So now since it's square tied, then this is going to be 0.8 and phi is going to be 0.65. So this is my phi, and this is what we used in that latest provision. Okay. Now the equation that we developed was 0.85 F prime C, area gross minus total area of steel plus Fy area of steel. Now P ultimate, we calculated that to be 2,280 kilonewtons, but since I'm dealing here with megapascals, I'm dividing this by 1,000 to convert that into million newtons. If you don't do that, you will get some very weird answers. Okay, now I'm assuming my area of steel to be 2%, so this is going to be area gross minus 2% area gross plus 280 times 0.02, 2% of the gross area. If you solve that, I'm going to get a gross area of 0.196, 0.2 meters square. Okay. Now here I'm going to assume a square column. You could also assume a ratio like we did from 2 to 2.5. Same thing applies here as well. So if it's going to be square, then B is going to equal to H. It's going to be equal to square root of this area, and that's going to be 0.44 meter. Here I would like to interject something. Here with columns, by the way, you do not have to go up, let's say, to the nearest number. Also, you could also go down another multiples of 50 millimeters. So here I could use 0.45 times 0.45, and you could also use 0.4 times 0.4. And I will leave that up to you to tell me what happens if you use 0.4 times 0.4. Obviously, the first thing is going to, you notice, is going to affect the area of steel. But here I chose to go with 45 centimeters by 45 centimeters. 2% of that, or area gross, is now going to be 0.02 meters square. Okay, I mean that's the area gross. I'll take that back. There's no 2% here. Now, again, going back to the same equation to come up with the area of steel. So don't multiply this with 2%. Actually calculate the required area of steel based on this. So now 2.28, which was my 2000 divided by 1000, 0.8 times 0.65. Here I'm using my new area gross. The only unknown is going to be my area of steel. So for that, this is my area of steel, which will give me 8,525, and that's a gross ratio of almost 2%. And the reason why this is close to 2%, because this is actually close to what we calculated. Have you used 40 centimeters by 40 centimeters? Obviously, you're not going to get 2%. You're probably going to get somewhat larger ratio, maybe 2.5, 2.4%. Again, here it's kind of your choice whether you want to increase the area of concrete or use more steel, depending on which one is cheaper at the time of your design. Go for it. Okay. Now I have to design my ties. I'm going to use again phi 10 because I must. Spacing is again 48 times the diameter of my tie, so that's 48 centimeters. It's going to be 16 times the diameter of the longitudinal bar, which was 25, which is 2.5, and that would be 40. My least dimension, well, here, since it is a square, it's going to be the same, so it's going to be 45. The minimum of that is 40 centimeters, so I'm going to use phi 10 at 40 centimeters. Obviously, I did not give you any information of the aggregate, so you will not be able to calculate that in here in this particular example. Moving on to another example, here we're going to design a round spiral column, and that's going to support a load of 800 kilonewton, including self-weight, and an axial live load of 1000 kilonewton. F prime C is going to be 20, Fy 420. Assume a total percentage again here 2%. I'm using the same technique again. P ultimate is going to be 1.2 dead load, Z plus 1.6 live load, and we're going to get about 2500 kilonewton. Now the only difference here, phi, is 0.75 because it's a spiral load, spiral reinforced lateral tie, lateral instead of a square tie, and that also goes from 0.8 to 0.85. So for square or rectangular ties, this was 0.8 and phi was 0.65. For spiral, this is now 0.85 and phi is 0.75. Now again, same equation, area gross minus the area of steel. Area of steel is 2%, and the only unknown here become area gross, and here I'm having 0.1602. Area gross is pi d squared over 4, and the diameter is 0.452 meters. Here I'm shooting up all the way to 50. So I'm going to use a 50 centimeter diameter circular column. Again, here, if you want to choose 45, you can. Try that, please, and see how that will translate into the difference in your reinforcement ratio. Okay, now I need to figure out what my area of steel is, so I go back to the same equation. Again, always, once you define that gross area, go back to the same equation and find out what the actual steel reinforcement is going to be. Okay, so as you've seen here, this is now my area of steel. I'm going to use 6 phi 22, right, which is again the minimum for a spiral. Now you've noticed that because I've used the larger concrete diameter, my steel reinforcement ratio is almost 1%, although we started with 2%. Okay, but again, I went from 45 to 50. I went to the higher range, so that enabled me to have a lower reinforcement ratio. Okay, and that will give me a P ultimate of 2600, again very close to my 25, so I am okay. So now I need to design my spiral according to the ACI code, and let's do that. Now this is purely from mathematical books. The reinforcement ratio, the spiral ratio, let me call it rho s, is simply the volume of a spiral in one loop. Okay, so this here is one loop divided by the volume of concrete core for a pitch. Okay, so now that volume of a spiral is going to be the area of this deformed spiral. Okay, so if I'm using phi 10, it's going to be the area of phi 10 times pi times dc. Now dc is measured as the outer diameter of the spiral. So let's say I have 4 columns. My concrete cover is 40 millimeters each side. So my DC will be technically this 40, and this is my 40. So it will be the total diameter D, or the outer diameter minus my covers, and we do not include phi of the spiral. So that's the definition of DC right here. So, and the volume of one concrete pitch is going to be pi times DC core inside times the spacing divided by 4. So the rho s that I'll be using actually is this equation, so we're going to use that equation. Okay, now DC again is going to be my diameter, which was 1/2, which we got by the design, minus the cover from both sides. So DC is going to be 0.42. So the area of the core concrete is going to be just pi d square over 4, and that's about 0.1385 meter square. Now we said that the ACI code gave me a minimum reinforcement, a minimum spiral ratio, which was 0.45 area gross divided by area core for the concrete minus 1 f prime c over fyt. Now 0.45 is here. Gross area is what we calculated before. The ACH, which is what we calculated also before, f prime c was 20 divided by 420. Then this is my rho s. Now if I use that with the previously developed equation for rho s, then I can calculate the required spacing. Okay, so now here's the spacing s is my unknown. It's just going to be simply 4as dc minus diameter of the bar divided by dc square rho s. So 4 is here. Again, this is the area of 1, which in my case was phi 10. So it's going to be 0.785 times dc, which was 42, minus 1. Then divide that by 42 square, and this gives me a value of 8.16 centimeters, which is more than 7.5 centimeters. So I have to use 7.5 centimeters. So the only difference when we design a spiral reinforced concrete column, we have to do that extra additional step of calculating the spacing. For rectangular tight columns, we only need to adhere by the 3 or 4 conditions that we explained in the example before. And that will end this part of axial loaded columns. And you guys have a nice day and stay safe.